just go.
Alrighty, welcome to lecture 2. This time I'm not sick, therefore, well, I'm not getting off of being sick, therefore, hopefully there'll be a lot more energy this time. Thank you to everyone who got checked off. If you didn't get it checked off, I think you're not here right now, but you'll get checked off soon, trust. Today we're going to be talking about digital logic design. So if you take an M16, this should be a review for you or a crash course on it in less than an hour. But if you're bored, hopefully the memes are good, are enjoyable, and if you're not bored, hopefully you'll be better at M16 later. First, we got a couple announcements for you. Andrew?
So we got our through-hole soldering workshop. That's going to be this Thursday, October 28th. You got to fill out your Google Forms, and hopefully you've done that by now. We also have our GB info session. This is going to be this Friday, October 29th, actually right here in the Shannon room at 7 p.m. This is going to be where you guys make your IEEE family. Join my GB, it's going to be the best one. We're going to have 2 generations of DAV leads, hopefully a third. We also have Alumni Mentorship program, which is AMP, which is where we get to have you guys connected with IEEE alumni. Great program, great way to make connections in the industry, and hopefully, learn more about the history of IEEE. Then we also have lab books. We're going to be talking about that later in the lecture. Lab books could help you guys buy some food in the lab, as well as like some other fun little prizes. And we still have not had anyone look for a cardboard cutout of Brandon yet. Next slide.
So a little more information on GB. GB stands for General Board. This means, so essentially General Board, the idea is like, we have Officer Board, Projects Board, Admin Board, and then you have General Board. So you actually get to lead events of your own in a group, and you get to work with other people. You get to basically, it's just like a smaller community within IEEE. So you get to meet all these people, become friends with them, hopefully, and then do other leadership events within IEEE, like leading events. Also, some GBs like to do projects. Other GBs are more social, or like social only oriented. But you get to pick a GB of your choice. So the info session for this is on Friday, as you can see on the poster. There's a Facebook event. I think it'll be announced in Discord multiple times. So make sure to come out, even if you're not too interested. Trust me, you'll be interested if you come to the info session. Yeah, and then you can see 2 hooligans highlighted in the picture. We were actually both in the same GB freshman year. Now we're both DAV leads, so what does that really mean, right? Maybe you can lead DAV too if you join GB. You don't have to, but you should. And then AMP, so I don't know if you've heard about AMP. This was actually piloted last year, the Alumni Mentorship program. So you get paired with an alumni of your choice. Well, your choice if you pick one, or we'll pair you. Kat, the secretary, will pair you. And it's a one-to-one like mentorship connection, kind of like the one that UCLA does through UCLA 1, the alumni program. But we do it all with IEEE alumni, so you get specific like ECE or CS like oriented advice. So fill out the form, it's in the lecture slides. If you want a mentor, Cal will be more than happy to give you a mentor. Finally, lab books.
Lab books. So if you do DAV, you earn cash. You get lab books you can spend on treats in the lab, as well as some other little fun things. We're going to do $30 in total per lab. So that's $30 if you finish before the deadline, so you guys don't come to us on the day that checkoffs are due. Come to get checkoffs done before, please. $25 if you come and get checked off the day of checkoffs. $0 if you don't get checked off on time. Now that's going to be an extra $10 for our optional week 10 through winter quarter lab, which is going to be on state machines. State machines are really, really important, and it's just something we just don't have time for this quarter to teach you guys the fundamentals of. So we're hoping to just put it over winter. This is a bit of a incentive to do the optional lab, but it's also just really cool, so you should do it. That totals into 100 lab books, which is able to get you quite a lot of stuff. Yeah. Next slide.
Okay. All right. So this slide is really based on all the errors that we found during Lab 1. A lot of you may have ran into these issues. If you did, good. Hopefully you learned from them. If you didn't run into these issues, hopefully you don't run into them later. if any of these issues occur to you, like these are the fixes that we found, some of them we should have provided to you before, like the fact that if you use $stop, many of you have found out that like it closes your simulation if you click yes. Two fixes to that are either to keep using stop and click no, or you can switch it to $finish. In that case, what it does is it finishes the run, but it doesn't close the simulation. Stop stops simulating overall. So that's the difference. And then the rest are all errors that I ran into. You can just read through later. I think some of the important ones though, if you ever get to Model Sim, you try to simulate and your work folder is empty, make sure you check the transcript in Model Sim. It'll show you the error. Sometimes that error, so what happens is like Hortus will try to synthesize your net list like we talked about, so all your gates, but it won't give you an error because like in synthesis it seems okay. But when you try to simulate it, that's when Model Sim figures out like there's something wrong with your design. Like I think a lot of you might have figured out like the netf error is like disconnected or something like that. So that will show up only in your transcript. So make sure you read the transcript if that is the error you get. So that's really important. Other than that, the rest you can treat. Moving on. Today's plan. So we're here for digital logic. So many of you might be asking what digital logic is. We'll cover that. And then we're going to go into two main branches of digital logic, combinational and sequential. And then we're going to talk about building blocks in terms like digital logic building blocks that you can go into. And finally, Andrew will give you a little rundown of lab 2. So let's get right into it. Before we get right into it, so I told you the timeline. Every time we're just going to do a little check-in. So we finished lab 1, right? Verilog basics. Now we're doing digital logic. So this is going to keep building your foundation that you need to. It's just like your Verilog skill set to design FPGA circuitry. So right now, that's what we're going into, and this is just more of the timeline yet again. So digital logic, what is it, and what can we do with it?
So this is a bit of a review from lecture 1, which is bits. Bits stores ones and zeros. It's the basic building block of every computer. Just gotta learn how to use them. You gotta think it requires attention for every bit computation in the circuit. Yeah, pretty much it. You guys know bits. Next slide. Now on to logic gates. It's something a bit less review. It's the bait and stick unit for FPGA circuits. It happens with a couple transistors in special little ways that you're going to learn later in your college lifetime. It makes the bits do what you want. So for example, we have this AND gate, and this AND gate is only outputs a 1 when both the 1 and the 0 and the second input are both 1s. Then you have the NAND gate, which is the exact opposite, the not AND, right? Then you have OR. Can someone tell me what OR gate does? Can someone tell me what OR gate does? Okay, cool. This is for you. Okay. We can't have it in the shade room right now.
But we will give it to you after.
Yeah. All right. So what about the NOR gate?
The opposite of the OR gate, so it only outputs a 1 when both inputs are 0.
Only outputs a 1 when both inputs are 0. Perfect. Great job, guys. All right. I think we're done with that. Next slide.
Yeah. More can be opportunities later.
Oh, we skipped a slide.
We did.
There we go. So wires and registers. You guys had a bit of trouble with this in lab 1. This was quite intentional, actually. We wanted you guys to, struggle with wires and registers. So wires, they're information carriers, right? They just are one thing to the next thing. There's no storage with them, right? Registers, on the other hand, store information. It's very important. They store information. It's like an int or any sort of variable in a normal programming language, right? Registers use clock and reset signals, but not Verilog registers. Registers in hardware use clock and reset signals. It's very, very important to know the difference between hardware registers and Verilog registers, right? So they also update values based off of the clock cycles, only in hardware. This is all hardware stuff, right? We're gonna get later in the lecture, you're gonna learn about the Verilog register, which is completely different from a hardware register, right? This is something that is very often confused for people starting out with Verilog. All right, next slide.
Alright, before next slide. Candy opportunity number 3. So, you have assign statements and you have always app blocks. Which one can you use with wires and which one do you use with registers? Alright, Tobias.
The assign is for the wires, and then for inside the always loops is for the registers.
Alright, nice. So, keep him in your brain too.
Gonna have a lot of
I'm
people.
creating a memory stack in Andrew's mind of how many people get candy. Good question.
I had a question, like inside the always blocks, there's the blocked and the non-blocked
Perfect.
equals. Like, what's the difference between them?
We're getting
there.
Okay.
Good question. Alright, that's in like 10 slides.
Okay.
Any other questions yet? Okay, cool.
All right, combinational logic. So combinational logic is where you combine your OR gates to your logical gates in order to do certain things. So this is where you do bitwise computations, which is what Verilog uses as the placeholder for an OR gate. So if you guys know C and the bitwise OR, which is like the single pipe, that is an OR gate in Verilog, right? The AND would be a bitwise and that would be the AND gate in Verilog. So this combinational logic only depends with the input and the output. There's nothing that loops back into itself that tells it what to do. And usually it doesn't require a clock signal. Not always, usually. Combinational logic is also always running. There's no specific instructions that force it to loop back in on itself and have any sort of delays like that. Next slide, please.
Specifically, he says combinational, there's no looping back, because if you create a combinational loop, just think about the problem. So if you have like an AND gate that you like connect back on itself, it creates like just the circuit, you can't really like confuse a circuit like that. It doesn't really make sense to do that because you're running a connection that like should not loop back on itself. So always be considerate of not creating combinational loops because the things are like updating continuously. So like it'll just create a problem. I think the AND gate is a bad example. I'll think of a better one later hopefully. But
So
you can create a combinational loop. Yeah.
if you think of your problems that happened in lab 1, if you remember, F was in the always block and F was added in on itself. So that was, and it wasn't initialized, right? It wasn't starting out with any value, and so it would just continuously be incorrect, right? That's something that you can't fix with combinational logic. You'd have to actually convert that into some sort of sequential logic system. Next slide.
Okay, so combinational logic, no registers, just gates and wires. So what can we build with gates and wires? The 3 main things we're talking about are muxes, so multiplexers, encoders, and decoders. So multiplexers, we'll do a whole exercise on, but essentially you get to choose out of like multiple inputs, use a couple select bits, and you get to choose which output goes through. So this is really useful. Technically, when all of you fixed the F initialization, what you can think of it as like, what's happening is that at the very first initialization, there's kind of like a mux that basically says like if it's the first run or in the initial statement piece, it's like the input is going to be a 0, right? But then in any other stage, it's basically getting like F plus 1. So you're basically muxing that in the hardware to say like that you can choose between 2 inputs. Otherwise, like if you just said it's 0 at the beginning, it's not really like C++ where like that runs first and then later it runs like F equals F plus 1. It has to be muxed. So muxes are really useful because like otherwise every like wire register you do can always only have 1 input. So it doesn't really you can't ever like change what kind of input you're giving it. And then encoders and decoders are completely different thinking style. You can see them on the bottom 4 images. So an encoder takes 1 hot inputs and changes them to binary. So 1 hot we'll discuss in the next slide, but it's basically an encoding scheme for numbers where like for every number only 1 bit can be hot or on. And then binary, it's just binary. So encoder, so you just have to keep track of the fact that encoder means you're going from one hot to binary, and decoder means you're going from binary to one hot, which may be confusing because like you think like binary is your regular scheme, and then you're encoding into one hot, but it's actually the opposite. Okay.
Before we go to the next slide, can someone tell me what this is right here?
It's the Knox.
All right, and what can that be analogous to in system Verilog? If statement. All right, good job.
Any other questions on this slide? Okay. So, okay, as I said, one hot encoding. For every number, you have 1 bit hot or on, and so that means you need n bits to represent n numbers, which is kind of inefficient because in binary you need like log base 2 or whatever. But since every number needs its own unique encoding, you're gonna need a lot more bits to represent it. So similar to said before, like it can get kind of confusing. Where one thing that can get confusing is that you can say like one hot and binary are both encoding schemes because like they're like ways of representing a number. But keep in mind an encoder is always one hot to binary. But it's not like you need to memorize this. You can always just literally look up an encoder and it'll tell you which one. But just keep that in mind. So that's really all about one hot encoding. The use case of this is kind of cool, where like you can see in this little table. So like if you index every number to like a different, like let's say you have a variable in your computer that's like keeping track of, I don't know, what kind of animal you have, and then like different people can have like the same animal, right? Instead of having to write that out in binary, if you just do it in one hot, you always instantly know which animal to have because like that bit is on. So like if you just said like 4, and you would have to like look in the table to see line, or you could just like have a row of bits, and whichever bit is on, you know that is like what is on. So it's just a different way of representing numbers that's like better visually. Because a computer cannot literally just store a bit that says dot, you know, so you need like a number. Question? Okay.
So here's our mux breakdown. So if you were to look at a mux as just a logical block, you'd see this right here, which this is a 4 times by 1 mux.
Or 421.
It should be a 421, yeah. But this is a 421 mux with 2 select bits and 4 inputs. So the select bits go from 0, 1, 2 to 3, and that's selecting the 0, 1, 2, or 3 of the input. So in order to do that with logical gates, you do this right here. So you have your 2 select bits, which are A and B, lowercase a and b, and your inputs are uppercase a through d, with your output here. After a bit of working on it by yourself, you guys should be able to figure this out and form the same truth table as right there in the middle. Next slide, please. Ooh, exercise, alrighty.
Alright, we're gonna do a little bit of whiteboarding. But just think about the question. How can we build an 8-to-1 mux out of 2-to-1 mux? So 2-to-1 mux means 2 inputs, 1 output. And you can build an 8-to-1, so 8 inputs to 1 output with just 2-to-1 muxes.
Alrighty.
We're hoping we can have someone volunteer, or like people can come up and like put stages down or something.
3 candies for anyone to do it.
You can take a sec to like think about it first. You don't have to instantly come up and just give us the answer. But this is more of like a, instead of us talking, just get to think. Or if you're uncomfortable, you can also just like tell us what to draw, and Andrew will bring out his beautiful handwriting.
Yeah.
I'll speak it. So I think you need 4 2-to-1 muxes so that you can get 8 inputs.
Okay. So like, in what order?
I would just like draw them first.
Okay.
Bigger, right? You can do way bigger than that.
Okay.
So what? I think you
Oh my god. Is this even visible? Yeah, so I thought. Lights.
like this.
Yeah, I guess. And then each of those 2-to-1 muxes has one select bit, right?
Right, so we have in 1, 2, or 0, because we're engineers apparently. 1, 2, 3, 4, 5, 6, 7. And each of these has our one select bit. Alrighty, what next?
I would combine all the unselect bits into one wire,
Okay.
so that like this one would like.
Wait, what do you mean by connect
Like-
all?
Like I would have them all be controlled by the same thing, correct? Because an 8-to-1 mux is gonna have a 3-bit selector.
Yes, yes. So
Okay.
which bit should be connected?
Oh, the least significant one.
Yes. Nice. Someone else? Yeah.
Actually, if
You would have 2 more muxes, yeah, and then the select for those muxes would be like the 2 original selects ANDed.
Wait.
Yeah, and like similar for
Select 0 and select 0.
select 0 and select like the next select of. Wait, are we using the same select for
Oops.
all 4 of those original
Wait,
muxes?
just to be clear, let's write out the input and then the select 3 bits.
Right, so select is 3 bits.
2, 0.
So it's 2 to 0. So the 0th bit, there's the 1th bit and there's the 2nd bit, right? So each of these can be on or off in any configuration based off of this right here. So you have your first stage, which is all at selective 0, which is going to be able to select one of these 4 possible configurations based off of what numbers these are as well, right? So you're going to see that like if you have select 0 on, and it's select 0 is equal to 1, then it's going to do in 1, in 3, in 5, in 7, and those are all going to be output to this next set of muxes, right? Then you have select bit 1, which is going to be what selects from this stage here, which is either going to be on, if it's 1, then it's going to be the second input. If it's 0, then it's going to be the first input, right? So what should this bit be right here?
Select 0 and select 1.
Just select 1. Since select 0 is already taking care of the logic on that side. Right? So we're gonna have something like, looks like this, with an output here. Oh my.
I'll take a picture of this stuff.
And final layer.
Yeah, alright, final stage. I'm sure you can see a pattern here.
Just 1 mux and select 2.
Is it that?
Yes.
Alright.
Well, I think yeah, I get it.
And what's the select bit? 2. Alrighty. Would someone like an example of how this went over? You guys don't get it, okay. There you go. So we have the example of 101, right? So this is select bit 0, or this is select bit 0 right here, right? Select bit 0 is turned on. So that means that we're only going to be able to use 1, 3, 5, and 7. Then we have select bit 0, which is off. Or select bit 1, which is off, right? So that means we're only going to be taking from this side right here, 1, 2. Then we have select bit 2, which is on. So that means we're going to have right here. So now if we follow, based off of follow ourselves back, we'll go woo. go woo. Shit. We'll go woo. All the way back to select set 5. So input 5 would be selected when we have in binary this would be 1, 2, 4. So it turns out input 5 selects or select 5 selects input 5.
Congratulations. Teamwork makes the dream work. Any questions about what we just did? Look at the picture. Alright, I'll take that.
Okay. So
Oh, yeah.
here's the final answer right here.
That's just a solution for anyone who's not here.
It's a bit cleaner.
What do you mean? That was an amazing job. Everyone clap for Andrew's. You get candy now.
Yeah.
Alright, so you did combinational logic, but now you have to worry about clocking. So that means we're getting into sequential logic, and by the term name sequential, you kind of see like instructions kind of happen one after another. So it's not exactly like C++ programming where it's like an instruction occurs. It's just we clock stuff to happen one after another. So you kind of think of it as like all you're doing is adding a register. So then the register stores where the circuit kind of is at, which is called a state. And so once you're at that state, you go to the next state by going through some combinational logic that calculates like what the next thing should be. So a simple example is like your F incrementer. F was just keeping some sort of number as its state, and then it would keep incrementing it, and the adder incrementation would be some combinational logic. So sequential logic actually uses combinational logic as a subset. It's really just saying that now instead of just gates and wires, we're going to add registers to it. So hopefully you can remember this because we just added memory to sequential logic. Okay, so I say it allows for ordering and delaying instructions. By this I kind of just mean in combinational logic everything happens like immediately. You change the input, you immediately change the output. Whereas in sequential logic you can do stuff like pipelining. If you ever like taken like computer architecture classes where like stuff gets like propagated through the circuit, which you can't do with combinational. So this adds a lot of like functionality that we just didn't have before. So moving on.
It's leak code time, guys. So this sort of stuff is only really going to be used in interviews. We don't really quiz you guys on it, but this stuff is really, really useful. You're going to learn a lot about this in M16. And Shinta, you want to take this away?
Yeah, so in Verilog, like when we program, we don't, at least for us, we're not going to be thinking about clocking too generously or like too specifically. But it's just nice to know what setup and hold times are. So in a register needs a value to stay stable both before and after a clock tick. So when the value comes in, it has to stay stable for just a setup time or like a certain amount of, I don't know, like maybe it's like nanoseconds, right? Before the register can like accept that value. And then it also has to stay stable after, because while it's like processing the fact that it just changed its input into its output, it needs that value to stay the same. So if you switch from like a 1 to 0, you can see the violations here. Like if the value changes from 0 to 1 during the setup time, then like it's kind of undefined whether the register will take in the 0 or the 1. And if the value changes from 0 to 1 after, like in the hold time, it's also undefined what's gonna happen. So you just want to make sure, like, if you're ever working on like straight up insanely clocked RTO later, you want to make sure that setup and hold time are met. And I'm pretty sure this is like an interview question for a lot of like Verilog kind of jobs. So this is just good to know. And then Sadan actually gave me this in the summer. It's actually a really nice example of combinational sequential logic. So the combinational lock, right? It just has 4 inputs, and as soon as you reach the right combo, it opens. So your output is basically just like some sort of logic gates on like what numbers you're at, what numbers your inputs are at. But then sequential, you have to do it like one by one. So it has to store whether you got to the right input, and then if you got to the right input 2, and then right input 3. And as soon as you break one of them, the lock's gonna lock again. You got to reset the whole process, right? So this is kind of like an easy way to think about combinational or sequential logic if you ever need to. or if you need to explain it to like, if there's someone asks you like explain it to a fourth grader, I think this would work. I don't know if because I think fourth graders have middle school lockers, but I honestly forgot. Okay. So another checkpoint for you guys. What does this do? Remember, candy's on the line. Tobias already answered like 15
Alright,
questions.
Tobias can't answer anymore. Sorry, man. Someone who hasn't answered yet. Corwin.
It adds by one every clock.
Okay, so what is this going to be after 3 clock ticks?
N+3. Or like the initial value at D.
Perfect. Yep. So, follow-up question, is this combinational or sequential logic?
This is sequential.
Right. Perfect. Great job.
Wait, what is DQ?
Sorry?
What is DQ?
DQ is a register. So you have this clock input is going to be controlling this register, and N is only going to be taking the N is only going to be loaded into this register at every clock tick, right? So after 1 clock tick, this is say N is equal to 1. Then it goes N is equal to 1. You have a clock tick, and this side of N is going to be set to 1. Then it goes all the way back around, and then this side of N is set to 2, right? Then the next clock tick flips. This is going to store 2, and it's going to go all the way around, and then store 3 on, or it's only going to set this side to 3. But this is still going to be 2 until the next clock tick, right? Okay. Any
D-
questions?
D is just the input and Q is the output. If that's what you're asking. Yeah, of the flip flop. Alright. So now we covered all this conceptually, but now I gotta do it in Verilog, right? Because you gotta write code. So let's get into the actual code. This is just a little bit of a review on wires and registers. Now you can kind of see that wires are useful for both combinational and sequential logic. Registers are useful for sequential logic. Little confusing thing here though is that regs in Verilog are not, they don't necessarily have to be registers like a sequential register in hardware. You can, we'll cover this later, but you can actually do a combinational always add block that will, you'll have to use a register because only registers can be, like the values can be changed within an always block. However, it's basically creating a wire in hardware, and so we'll cover that later. But just, this is just a good general practice. It's just that wires you use sign, and then registers you use always blocks. You can also use integers to just like store numbers that you're not necessarily putting in your circuit. They're just like kind of parameters you want, and those are just like always inputs. I think we covered this in the last lecture too. It's just a good review.
For case statements, like, is it safer to do it in that sort of format, like the 3 block tree, and then like give like the binary, or like it's using like 0, 1, 2? Is that?
It automatically does a conversion really, so it's not that big a deal.
I think you'll see in Cordis, it'll say that I think it's like the literal or something, or like the 32-bit integer input was given, and it was like cut down, it was truncated to the register's like 4-bit value or something like that. So yeah, it'll automatically do. Right. Okay, so I just said that we're going to cover combinational or sequential always blocks, and here it is. So this might be a little confusing at first. There's actually a really good HDL bits like example on this, but the kind of cool thing is that we kind of talked about always add blocks as like it's always going to be sequential, as in you're always going to be like always at a pause edge of a clock, and that means it'll update a register. You can actually do a combinational always add block too. This is just like sometimes you just don't want to do an assign because like maybe like here you have like multiple, like a if condition with different things happening, or like your changes can happen in multiple different like input changes, like A or B or select can change, and you want the always add block to trigger at those signal changes, whereas an assign statement is like always happening, right? So you can kind of change the wire, like a wire combinationally, but at different input changes by declaring it as a register and then changing it in always add block. So that's like kind of a interesting little niche thing about Verilog. Once you start doing it, it'll make more sense. If you have a question, you can ask, but this is just good to know that an always add block does not always have to be like clocked. You can change it based on any signal, and if it's not a clock signal, it's not going to be sequential per se.
Next slide. So, this guy from University of Tallinn in Estonia, reg is not a flip-flop. He obviously knows Verilog, unlike he's one of the very few people that know Verilog. So anyways, we found this on the forum and thought it was funny, so. All right, on to assignment. So we have non-blocking and blocking assignments. So non-blocking right here is parallel and sequential circuits. So this right here, you can see that there's A is assigned to B right here, and then there's a delay, but it's still assigned, right? Whereas here, you can see that this blocking statement is for procedural and combinational logics. And so you can see here that you have an actual 5-second delay, then, or you have your 5-second delay right here, then a 10-second delay immediately after, right? That's not good. Whereas this one, you have your 5-second delay, and then your 10-second delay based off the same assignment, right? Essentially, this like little arrow says like, okay, go to the next instruction while I'm still completing this already, right? So if you were to have like 2 wires going into something, into 2 separate things, and you want those to happen in parallel, you'd use a non-blocking assignment. Anything to add?
Yeah, so, okay, so I know, like, Bob asked a question about this. So, an important thing to keep track of here, the delay is important because, like, the delays are happening procedurally. However, even more important is the fact that you can see the value of C is actually different based on which one you use. So, if you do A equals B and C equals A in parallel, what it's going to do is it's going to give A the value of B, but still give C the value of A that, like, A had before. So in this case, like A was, I think A was 1 before. Yeah, A was 1 before, B was 2. So C gets the value of A before it was changed, right? I don't know if you can do this in like C++ because stuff is always procedural, but non-blocking allows you to run stuff in parallel, so everything's updating at like the same time, or like not necessarily the same time because the delays are different, but it's still happening like you're thinking in terms of the wiring. Whereas what happens in blocking is it's going to be more like, so you're going to have like a wire between, so think of A, B, and C as registers. What's going to happen is A is going to be a register with an input that's B, right? And so so it'll take input from B and become it. And then what's going to happen is after another delay, there's a register C that's going to take this value from A. So that's blocking because like they're all like in a line basically. But then if you do it in parallel, what happens is A is going to have an input C, but it's also going to have like an output B that it's going to have an input B, and then C is going to have an input A. But it's like they're not exactly. I think it'd be better if you draw this out.
Yeah, I was gonna say.
I don't think they're not like put in a line per se. So you need to draw this like fully centralized.
Right. So you have your non-blocking, where you have A and it was B, right? Or C?
A, B, C.
So if you see here, right? Is that correct?
Something's definitely wrong here.
Yeah. Something's definitely wrong here.
Wait, just turn the thing on first. A becomes B, C becomes A. Alright, so the register for this is gonna be the register for A. And A becomes B, right? So the input here is gonna be B. And then C is gonna get the value of A. So I guess the output here goes into the register C. And in non-blocking, what happens here is like
You have A going to a different thing at the same time, or this is.
Yeah, it's like this wire where the connection between A and C is kind of like independent of this connection. So like it doesn't really make sense. I think that there might even be 2 registers when this is done in hardware, or maybe a mux. But like, okay, blocking is the easy one. So if you're doing the blocking example, this is gonna, so like the first update happens at at cycle 5, right? Let's say this gets updated, and then at cycle 15, this gets updated. So then this propagates here, and then the same thing propagates here, or like the updated value propagates here. But then in non-blocking, I think it actually would go in like 2 different lines. It's not a great place to draw.
Just on the side, I guess.
Yeah, so like B would propagate into A, we know that. And then C needs to get the value of A before it's changed. So like whatever output here, I think it would have its own like register that it's saved in that only updates after 10. So like A, maybe we could just say like gets stuck into an input into another register here. This is just like the previous A basically. And then that is what goes into C. So like, the thing is, the timings here get a little weird because this one is like, this takes 5, at 5 this updates, and then 10 seconds later, so it's like plus 10 seconds, this updates at 15. But over here, this update takes place at 5, but like, since it saved this, and this doesn't update at 5, this still has the value stored from A, or like it still has the value stored, like the previous value of A stored, since this didn't update. It's like updating on a different clock. So then at 15, or sorry, at 10, this is gonna push this value, or like at 10, this will take the input in. This is really a confusing explanation. Maybe it'd be better if we just had someone ask a question on like, it might have made sense before we started the drawing too.
So then, like, would you use non-blocking when like the things that you're doing are like independent of each other, or?
Yeah. So like, you have the input to like 2 separate things, completely separate, and you don't want them to happen like disjoint from each other. You want them to be able to happen at the same time. Then you would use non-blocking.
Okay.
You had a question to begin with, yeah.
I mean, I was just wondering, like in the blocking situation, why C updated after 15 seconds instead of after 10 seconds?
Right, so that's where you're waiting for this 5 seconds to be completely done.
Okay.
And then essentially it's like executing this entire thing, waiting for the semicolon, and then going to the next thing, right?
And those are representing 2 registers, right?
Yes.
So then after that, does it continue just doing 5, wait 5, then update A, then wait 10 and update C, and then, or does it then start running in parallel?
No, so this is just an initial block, so it only happens once.
Oh, okay.
And it's not gonna like continue going over and over again, it's just this one, seeing these 2 assignments, and then you're done.
If it was an always out block though, it wouldn't just switch from blocking to not blocking. It would stay blocking the every time it's run. Yeah. So it would take 15 seconds every time.
Do you have to use this notation for the delays in Verilog, or like in the middle between the equals and the B, or can you put it somewhere else?
No, so in this situation, you would have to use it for the example, because you'd want a delay to happen between your assignments, so that it would not assign properly, essentially.
Well, I think he's saying like you could put it here.
Right, but that would only work. That would still execute this properly at that point, because you have that delay that then blocks this.
Oh, right.
Go ahead.
So in the blocking, if like for some reason you have like A equals like #10B, then would C get A or B?
It would in the non-blocking or blocking.
In blocking.
In blocking, it would just push this chunk right here.
Yeah.
Would just be pushed back another 5 seconds, right? Because you're waiting the 5 seconds. You're waiting the 10 seconds or 10 nanoseconds for A, right? So that's gonna wait 10 nanoseconds. It's gonna execute. Then it's gonna go to the next statement. It's gonna wait 10 nanoseconds. Go like this, right? You know.
Wait, sorry.
Yeah, go ahead.
Go ahead.
What if it was a non-block?
Non-blocking. So now that would happen at the same time.
Yeah.
What it would get, I have no clue.
I think it's actually undefined.
Yeah, I think it is undefined. Cause yeah, go ahead.
What's the difference in A equals number 5B versus A equals B and then it's like
I'm sorry.
if instead of like A equals at number 5B, what if instead it was A equals B and then number 5?
Okay, so do you know like the difference in plus plus versus like x plus plus versus plus plus x in C?
I learned this but I forgot it.
Okay, so let's turn this off.
Yeah.
So x plus plus equals y. This does the assignment to x, so y would actually hold x, and then x would increment plus plus, right? That's the case that you were talking about, Enoch, where the delay is after. Whereas the case of the delay between the statements would be like a plus plus x, where x would iterate first, then it would be assigned to y, which is the same thing that is happening here, where it is delaying first, then being assigned to A. Okay.
These are some amazing questions. I'm sorry that our drawings got a little
Yeah.
suspicious.
We'll have to come up with some better way to draw
Yeah, I think I
boxes.
have an example. I can put a screenshot on the slides of the better register, like the registers for this.
Oh, so for like non-blocking, like even if you increase like the delay, like instead of like delay 10, like you increase like delay 20 or something, like C would still equal 1 at the end of it.
If you increase the delay by 20, it most definitely equal 1, right? Because then it never gets B by the time that it gets to this point.
Yeah, I guess I'm just a little confused because it's setting C to A after 10 cycles, but after 5 cycles, A is already being set to B. So why doesn't, right? Because A is updated after 5 cycles, and then after 10 cycles, C is updated to A. So why is it updated to the previously updated version of A?
Because it doesn't rely on this being executed, right?
Well, but he's saying like it did execute at 5 seconds.
Right, yeah. So it's like if you were to like
There's a possibility this exit could be wrong.
no,
Because
no, that's correct.
A would have updated.
It would have updated, but it doesn't matter because C starts updating before it even gets to that point. So this is already executing by the time that this gets assigned. So it never actually gets from A here, it gets from A in the previous value.
So like, if you switch the order of the statements, the same thing, who would do the same thing?
Yeah.
Yeah?
Yeah, because they're happening in parallel, so it wouldn't
Yeah.
make any difference.
Okay, so that's what helped me to think, to figure out like why C is still one.
Right. Oh, that makes sense. Cameron.
Yeah.
What was your name?
Maya?
Maya, that's right. So Maya actually had a good point here. She was saying that if you switch the order, then of the A assignment and the C assignment, they'd still be the same, right? Because they're both happening in parallel anyways. So there wouldn't actually be any difference between having it like this versus having it the other way around. Whereas there'd still be a delay of 5 and a delay of 10, and they each still have the same assignments.
Right, so does that mean that the assignment in C takes the input of A, like, at clock cycle 0 and then doesn't
Yes.
execute it until clock cycle 10?
Yes.
That's what it is.
Yeah, no, I get it.
Okay, cool. These are some tough questions, guys. Jeez. Go ahead.
So is there just like a delay that like builds up more and more and more the value of C when you ran it for like a long time?
It doesn't build up. Say that this initial block was an always block. So what would happen is that you'd have this being run, and then at 5, right here, would be another assignment to A. So yeah, I think that's what you're trying to say, right?
Yeah, like would like your delay build up, or would you just be getting like every like third value
So it'd be update here, then update here. So then you'd have update here, but then you have your C, which is only updating every 10 seconds, which is here. So then you'd have every other update of B would update C. Is that what you're trying to say?
Yeah, I think so. I was saying like if you change B, like in the middle of this, like not or like after 10 seconds,
Mm-hmm.
like are you gonna get like the delay just gonna build up, or like are you gonna skip over a value?
You're gonna skip over the value.
Okay.
Yeah. So in this situation right here, A is 1, and then this would be C is 1, and this would be, this next C would probably be the 2. If you just call this the 2 and this the 3, then it'd be the 3 that's being sent to the C, right?
Okay.
Okay. Yes.
Wait, but like, would there be undefined behavior if, because like, at timestamp 10, A would be switching to something else, and then C would also be switching to something else?
That's a good point. I don't know.
Okay.
I'd actually have to like give that a try, put it in model sim, and give it a go. Yeah. That's a
I
really
think
good
since
question.
it's doing the parallel thing, since it's storing the initial value of A, it wouldn't be undefined. Because like it would just take that initial value of A. Yeah, but this like the 5 over and over again thing, I think we do have to run in model 7 to figure out.
That's a really good question. Actually, I'm gonna go give that a try, and I'll post it in the Discord, and we'll see what happens. Alrighty. Any more questions? No? Alrighty. Time to move on. I'm glad you guys asked a lot of questions about that, because that's like this one thing that like a lot of people ask in interviews is the difference between blocking and non-blocking assignments. And now hopefully, if you understood half of what was going on, then you guys will be able to answer most of the interview questions that are asked.
Okay. So, okay. Now that we've done the hard stuff, this is just some easy operators this should be useful to know in Verilog. If you haven't learned this yet, there are some things you can do called concatenation and replication. So concatenation is you can take like bits from different input buses or nets, like different wires and registers, pick certain bits that they have, and then concatenate them, just like a string in other languages. So this would be basically the most significant bit of Y, or the most significant bits of Y would be from A, would be all of A, and then the second least significant bit would be the 0th bit of B, and then the least significant bit of Y would be the bit 1 of C. So you can like connect them. So this you'll be doing in the lab. And then the replication operator, it just basically you can just multiply out a bit. So you just like, it's kind of like sign extending. You can take, like here you take the 0th bit of B and you write it out 4 times, and you can concatenate it with other things. So like Y with the replication is going to be 3 bits longer than Y with the concatenation, right? Because we multiplied the 0th bit of B 4 times instead of just once.
So the syntax for the replication is just the red stuff right here, but in total this is all a concatenation with just a replication of 4 right here with the red.
Any questions there?
You won't have questions now? Yeah.
When it concatenates, does it like go from like left to right? So like the A with the B is left.
Yeah. So it is like that, and so actually you could use that to flip the bits. If you're really gonna do it by hand, you actually set like the most significant bit to the first end, or yeah. So you can set the most significant bit to the back end and the least significant bit to the first end. Puts it in order. Yeah.
For replication, like the order in which you have it, is it like multiplier and then like the bit that you're multiplying, or could it be like the other way around?
Multiplier goes first. It's kind of like when you write out like 8 apostrophe B 0 0 0, we just follow the same order.
Any more questions? Cool. Alrighty, now on to lab 2. We're almost done with the lecture, guys. So this lecture, we're going to be having you guys build the basic building blocks of digital logic. So we're going to have like muxes, decoders, encoders, Hopefully you guys saw that in the lecture slides. Hint, hint. We're also going to be making you guys work with sequential logic, so that's flip-flops, logic, flip-flops, clock dividers, and we're going to actually be building a Fibonacci sequence generator, which is very cool. You guys should do it, please. Please complete your assignment. You also have, you guys do test bench for each one of these guys. So when you're doing your test bench, keep in mind the edge cases that you'd want to test to make sure that your module works in all situations. Finally, please, please, please start early. Not only do you get those lab bucks, ooh, but you also learn a lot more than spending all night doing this. This is not something that can be done in an hour like lab 1. This is going to take a lot more than an hour. Alright, any questions? Spec will be released later tonight or early tomorrow morning. Depends on what we get done. Alright.
Yeah. These are just errors you can check if you have trouble with the lab. We'll add more to this if we see like people trouble. All right,
We're done. Okay, I can't hand you guys out candy in here, so as you guys are leaving, come get your candies. If you answer the question and want extra candy, if you ask the question and want extra candy, just let me know.